Hello everybody, this is Robert Parker from LizardTech, and hopefully everyone can hear me. I'm ready to get started. We're all ready to get started here, and we're talking today about raster images and their properties, and we'll talk a little bit about compression as well. And before we get started, just a little bit of details on the WebEx. If you have questions at any time, phone lines will be muted, so we'll keep those muted so that there's not a lot of sound in the background and things like that. But if you do have there's a chat feature in WebEx. There's a little button that says chat. You can press that. You can see the chat. You can send me a message. You can ask a question to me, and when appropriate to do so, I'll take time and I'll answer that question, as well as any other questions that might appear there. As many as I can get to. And at the end of the presentation, or we might set a pause when it makes sense when I'm talking about something, but at any time, just go ahead and ask your question in the chat when you think of it. They'll be muted. And again, this will be recorded, so if you do happen to miss out on this, and you have to leave early or something like that, we are hoping to put this on our YouTube page under LizardTech University. We will be posting on our website at www.lizardtech.com, so you should be able to access this later. In case, I'm going to go ahead and start sharing my screen with you. And so here we have our .com. My name is Robert Parker. I'm a sales engineer here at LizardTech. My email is there, rparker@lizardtech.com. You can contact me to ask more questions after the webinar is over, or if you just want to touch with me about different products I might talk about, things like that. So let's get started. Raster imagery. It's everywhere. This is the middle of a raster image here. Here at LizardTech, we commonly deal with geospatial imagery. It's always going to be pictures of the Earth or something like that, but not always. You know, it could be a picture thing. So what exactly do we mean by raster, though? Let's take a look at raster and what that means. Raster image is basically a grid. It's fixed width and height. And here you can see an example of a 4x7 grid. That's up this raster image. And each pixel in that grid, each little box in that grid has its own value. We've got some boxes there that are gray, some boxes that are blue. Kind of looks like a triangle there. So that image. And in contrast, we have some vector. It's often referred to as vector raster. Two different things. A vector is basically an algorithm. It's a set of instructions. So, for example, in this case, you can say, well, draw a line that's 1 unit long. That unit can be any size or any unit, meters, inches, millimeters, whatever the case may be. This instruction is draw a line 1 unit long, turn right 45 degrees, repeat that a couple of times, and fill it with red. And then we have another triangle. And this will be scaled to size when you compare it to raster, which is a fixed width and height with fixed values in there. The raster properties that we might talk about again here with this particular image, there are a lot of different in this area here, especially these properties are all displayed. Let's take a look at some of these properties. So we see file type here. That's pretty self-explanatory. There are a number of different kind of file types out there for raster imagery. TIFF is very common. JPEG is extremely common on the web, and GIF and PNG. This one happens to be a MISTID. That's a LizardTech proprietary format. Was also compressed. See another different property image, the file size. That's the amount of space it takes up on disk there. This one is actually quite large, nearly 2 gigabytes. We see another thing here, input image size, which we'll get into later, which is much larger than we see for the file size. So obviously this is a compressed image. So this is about 7 gigabytes uncompressed and 2 gigabytes as compressed size. We'll get to all of this later. Width and height, they're pretty self-explanatory. The image is over 100,000 pixels wide by 85,000 pixels tall. Goes back to the grid aspect of things. It's a fixed width and height. Those are the number of pixels in the image, and each one has its own color, basically. And then there's these three here, which are what I'll start talking about here. The bands, the data type, 8 bits, unsigned, number of levels, and also coordinate reference. That's something you'd only really see with geospatial imagery and the events of the image, the resolution. These things we'll all talk about here. So before we started, what I'm going to start with here is this concept of being an 8-bit unsigned image. We'll start right there. And of course, anytime if you have questions, the presentation here I'll turn off, and we'll get into 8-bit, talk about what it means to be 8-bit. So before we get started, here's a little joke. I'll let you on here. Before I continue, can everyone hear me? If you can hear me, just give me a quick yes in the chat there or something like that. If one or two of you can do that, that would be great. Okay, I got some yeses there. That's really nice. I just had heard from a few people that they didn't have any audio, so it's good that a ton of yeses there. So that's great. Okay, so that's good. And back to the presentation here. So I'll let you read this because I don't want to ruin the joke. Just read this sentence here, and then online. Those who and those who don't. So I got an alternative punchline for you, and I'm assuming there's lots of laughter going on in the background because you're all muted. We can't hear all that laughter, but that's okay. So here's the alternative punchline. From there, we'll go to, we'll get right into what it means to be an 8-bit image, which is unsigned, and variants of that. So let's binary here. All of pixels are represented by a binary number. Obviously, computing is done with binary numbers. And I can explain to you about it. We can get into that later if that question comes up. But for now, I'm going to assume that you have a basic understanding of what it means to be binary, or I'll give you a basic one. Each one of these columns here represents a bit, and a bit can either be 1 or 0. So we've got 1, 2, 3, 4, 5, 6, 7, 8 bits. Bits represents a value, and so, for example, if we have a bit in this area here, in this bit here, if it's a 1 or a 0, that represents a value of 1. So if there's a 1 there, that means that you've got 1. And in space here, if you have a 1 in this space, it represents a value of 2. So if you put these together, you had what looks like an 11 there, that would be a value of 3 because you would just add those together. So forth. So if you were to add all of them together, the highest value that you can get bit 255. That means basically, actually 256 total values if you count, 8 zeros. But the highest value you'll get here is 255. Now let's contrast that with 16-bit. If you have 16 bits, there's 16 bits here, then the high value you can get is over 1,000. So that's a very significant difference in the values that you can achieve. So 8-bit image means that each pixel is by 8 bits. And number, the 0 or the range of 0 to 255, it represents the intensity of a specific color. So, for example, if you had just a grayscale image, I've got block there, but you know, if you had a grayscale image, meaning that there was just one band, one color band, you'd have a range of 0 to 255 for each pixel, and that would mean like a value of 0 would just be black, like no intense color at all, whereas 255 would be white. It'd be the highest intensity that you could possibly have for that pixel. And so if you have all these pixels, each one's going to have different color values, and you get this grid of, and it starts to look like an image. You could take a black and white photo, which is actually a grayscale photo, and get a nice color image. An example of red there. So you could have a 0 to 255 of red, but we don't always in imagery deal with just one color. We have 3 colors. Now, before we get to that, we saw in Geo Express here, we saw that this wasn't just 8 bits, it was unsigned. So what does that mean to be unsigned? So we have a concept of what it means to be 8 bits, each represented by 8 bits. But what does it mean to be unsigned? So let's take a look at that. So an unsigned integer, and this is the most common that we see in imagery, is an integer that can only be positive. That means it's going to have a value from 0 to 255, 1, 2, 3, 4, 5, and so on. An integer, you know, not a decimal point or anything like that, but 255. That's what it means to be unsigned. So 8-bit, 16-bit would be 0 to over 65,000, but they'll all be positive integers. Now, a signed integer is either going to be positive or negative. In order to do that, so we still only have a range of 256 values. Now, the signed integer, what we're saying is we're going to have 0 point, and you know, from negative 128 to positive 128. And why would we do something like that? Well, because in our case, in geospatial imagery, we often do that because we have elevation data. It's going to be data that's below sea level. There's going to be data that's above sea level. And we're going to represent that in our imagery. And it's just very intuitive to use numbers to do that, to represent that are below sea level. So that's what it's to be signed and unsigned. And if we look back at our here, we see that it is so it's probably not elevation data. It's just positive integers. And when we look at it in the preview, we can see it is just like image. So now, let's get on to this part here, which says bands. Now, we'll talk about basically a 1-band image. When I was talking about grayscale, and I was talking about the range of 0 to 255, a 3-band image is just 3 of these. So we've got 3 different colors. Let's take a look deep pixel level here. So here we've got red, green, and blue. Now, this is because these in color station make all the colors that our eyes can see, a visual spectrum of the electromagnetic spectrum here. So see red, green, and blue, and I've got the numbers 255 in there for each of them, meaning they're all at their full intensity. And when that happens, we color white. Now, I've got it blown up here, but if you were to look with a magnifying glass at your monitor and you were to look at the pixels in your monitor, you would see little red and blue combinations, and those are your pixels in your monitor. A raster image, the numbers in that image, the binary numbers in that image, tell the monitor what to display, and it displays an intensity of red that's full intensity and green and blue full intensity. Now, for example, if we had the green and a 0 intensity red, we would just blue. So we'd say 255 intensity of blue, And you have different shades of blue as well if you had the lower value, anywhere in that range of 0 to 255. You'd have different darknesses and lightnesses of blue. And if you combine the different colors of red and green with that, you can get a full range of colors. In fact, you can get over 16 million colors, nearly 17 million colors. Just 56 cubed, 256 by 256. And the more bands you add, the more colors you're capable of producing. But of course, are capable of really noticing the colors in our visual spectrum light. So images can have multiple bands. Your model can only display 3 at a time. Interesting. So we do run into images that have multiple bands. For example, the most common is red. It's a very useful wavelength of light. It allows you to see thermal information visibly. So it's a very good thing that we don't see it with our eyes. Maybe certain animals do, but we don't. And we have devices that are capable of capturing that wavelength and storing that in an image that we can then represent using one of the 3 color bands that are capable of seeing. So there's always going to display some combination of red, green, and blue. However, you can say to the monitor, or you can see your image, and I do have an example of a multi-image here. Let's take this in depth here. Here's the band image. And I'm doing 3 bands at a time here. I have a little band selector here. Right now, 1, 2, and 3. That's what that looks like. That's natural color. So 1 is red, and 2 is green, and then 3 is blue. But I know that I've got infrared data here, and actually make the red color the intensity of infrared. And maybe all the different band combinations so that I have different intensities of my waveform. So here I've got band 4. So the red color is going to be the intensity of what's in my band 4, and I can change that to band 5, and that gives me different intensities of red and different information. I mean, over here, like for example, you stuff pop out there when the band combination there. It gives me different information, but based on what I've chosen. And if you look in that same spot and I change this to band 4, you see that stuff disappear. I mean, it doesn't stand out as much. So the different wavelengths that I've collected here give me information about the viewing. So you can have hundreds of bands. There's a full range of the electromagnetic spectrum here that you can capture and that you can put into a raster image. However, you can only display 3 of those at the same time. There's a special band that I want to talk about, and that's called or the alpha channel. Bands are often referred to as channels or arrays, but it means the same thing. And each band is only going to have a range based on, like we said, 8 or 16-bit. And if it's 8-bit, it's going to have a range of 0 to 255, etc. There's a special kind of band called an alpha band. Now, designated for transparency. I'll give you an example of this visually on my application there, Geo Express. So each pixel in an alpha band is about being represented by a color. It actually determines the opaqueness of all the pixels below. So whether the pixels below are visible or not, or if they or the amount of visibility that they have, the amount of transparency that they have. Let's say 4-pixel image here, a 2x2 image. So I've got 4 in this image. I've got an alpha band represented by this gray here. I've got a red band, a green band, and a blue band for the visible colors. It's just a standard 3-band image with red, green, and blue wavelengths. Now, here, the output is set to 255. There's one pixel in the corner here where the alpha band is set to 0. So because alpha band is at 255, those 3 pixels will display on my monitor. And because the alpha band is 0 in the corner there, that one little pixel won't display in my monitor. So I'll have this little L-shaped looking white L, backwards L there in my 2 inch world example of this using this. And this is why alpha is important, because you see this image here. Do you see the black around the edges there? This here edges are because an image to be a grid. A raster image has to be a grid. It can't be off shaped like that. I mean, you'll see that obviously not data we intend to include with our image. It's meant kind of outside the image. We can see that with our eyes, but I mean, technically, all of the pixels in the grid. So what we do is we have alpha. Now, in the liberty of adding an alpha band to this image, and when I do that, look at that image, you see that the black disappears, and so we have a nice clean back to our image. Even our image is oddly shaped. Actually, look at that alpha band. If I'm mode here, and individually, here's band 1. That's the red band. Intensity of the blue band. And so I got that mixed up. And then the alpha band. There's my white. And you can kind of black outline there of it. It's not perfect in this case. We generated it very quickly. But alpha band, all of that white gets through. But everything doesn't. I'm going to see that we want. An alpha band in a nutshell there. And it's very useful for things like that. So if you have an image that's compressed, it's going to be able to, no matter what compression has been done here, it's still going to be able to mask out that area there. But let's get into another property, which you kind of got a preview there as I zoomed out, and that'd be the resolution. So we have the resolution here. You see a 1 and a -1 there. What does that mean? And what is resolution anyway? Well, it has to do with the extent. And I use as an example this image here, which is a very large image, King County from 2009. Let's look at some of these numbers. We have image extents over here. Extent, the top extent, the right extent, the bottom extent. What are those numbers? Well, it's a geospatial imagery. This kind of gives us a clue right here. The coordinate reference system and a projection. And projections are something that are way beyond the topic for this presentation and for what we're about as basic raster image properties. However, we do intend to do a session on coordinate reference systems and projections, if you're interested, of course, in the future. However, so let's take a look. This UTM zone 10 north, this is what determines those numbers there. This could easily be a projection that you are all more familiar with, which would be the lat long coordinate system. 36 north and 122 west, something like that. But UTM coordinates, and what we're going to do to find the X solution is we'll take the right. Subtract the left from the right, and over there. And solution is 1. What I bet we'll get is 19,420. That's what we'll get when we subtract these, because the resolution is 1. Because basically, as I will show a little drawing here, the resolution is simply the geographic dimensions by the image pixel dimensions. So we take the width divided by the pixel width. That which is the right minus the left here, to the image width. That's this 113,420. Do that, we get 113.45 meters over pixels. The width, we get a value of 1, and that's our X resolution. X resolution because it's the width. Y resolution going top to bottom is some kind of thing. We're gonna divide that, and it's a negative number. If you'll recall, I'll put that in here again. It's a negative number because the value in geospace increase, but the pixel values decrease as you go up, because the top left corner is 0, and bigger as you go across the image. So it starts at 0, and then it goes all the way to 113,420. Start 0 in the top left corner, and as you go down, it goes away to, what was it, 84,870. So that you get 1 meter per pixel because you're dividing the meters by the pixels in Y meters. Real quickly here, I'll zoom to this. Because metadata of our action here, the unit is meters. And I'll circle that real quick so that you can see. It's beyond scope of this presentation to go too deep into projections there, but there you have it. 1 meter per pixel. It could just as easily be inches, or it could be a very small image, and it could be millimeters or something like that. But it's 1 meter per pixel. That's our resolution. We're taking the real world, we've taken a picture of it, and we're saying that each pixel represents 1 meter on the ground. So that's all right. Covered a lot of ground here, and let out. So to the final part of our presentation, and please, if you have questions, please don't hesitate to type them in the chat. I'd like to see a lot of questions. I'm hoping to see a lot of questions. It shows me that you're interested, paying attention, and there are no stupid questions. We've covered a lot of information here, and if you want to see more, I can always go further in depth. And I'll leave into this to answer questions. So look at this. Compression. Here we see, again, that the file size is 2 gigabytes. However, number here, this input image size, 26.9 gigabytes, nearly 27 gigabytes. What does that mean? Where does that come from again? So let's take a look here. Let's take a look at this. I've got a little formula that's always valid. That number that you saw, that 27 gigabytes, the uncompressed size. That number represents all needed to rent that image. Now, with that data, we can represent that with a smaller file size and reproduce all of that data. But the uncompressed image, the amount of data we need to represent this image is represented by the width, height in the image times the bits, and that would be, for example, a 5-pixel image by 1,000 pixel by 3 bands by 8 bits. And as we have, each image is represented by 8 bits, so that's a value of 0 to 255. Now, if there are 3 bands of this, then you're going to have to multiply that by 3. Here, this is your grid, this 5,000 by 5,000 grid. This is pixels that are in the image. So there are 5,000 by 1,000 pixels in each band. So that's why we're multiplying by the bands. And any of those pixels is represented by a value from 0 to 255 because it's 8-bit. So that brings us to approximately 600 million bits. and stuff like that for bits. We turn them into bytes. We turn that into kilobytes. We turn that into megabytes. We get 75 megabytes. This formula is always valid for the image. No, compress it. Size, this uncompressed image size will always be the same. Now, the only way it could change, for example, you crop it, then the width changes, then the height changes. Then would obviously this would be a smaller pixels here and here, and so the size would change for your cropped image. But if you don't crop the image, if you just compress it, you turn it into a JPEG or you turn it into a Mr. Sid or something like that, sure, the file size will change, but this uncompressed image size will never change. Never matter how much you compress it, because it's based on these factors which don't change. So it all makes sense. And let's take that a step further and look at compression ratios. So since this is a compressed image, this is in the Mr. Sid format, which is a compressed format, it has been compressed significantly here. 27 gigabytes down to nearly 2 gigabytes. So that's a significant compression. So let's take a look here. We have a compression ratio. What does that mean? And really here, it just means a division. So we're going to take the uncompressed size, which an example above was 75 megabytes, and we'll divide 20, and that gives us a 20-to-1 compression ratio, which turns out to be about 3.75 megabytes. So when all said and done, that software will look to make that image 20 times smaller, 3.5 megabytes. It will do its little algorithms and things like that to make that image that file size. If you chose a 40-to-1 compression ratio, it would divide by 40. The uncompressed file size divided by 40 results in 1.875 megabytes. Now, to do this, to get rid of some data, but it does it in a smart way so that it gets rid of that don't impact on the image. So that when you look at the image, you won't notice the difference between the compressed and the uncompressed. You'd look at this, and data that it got rid of, when it goes to reproduce that image, it puts similar enough data where you don't notice the difference. So to find the ratio used for compression, I have my image here, and I can see the raw size here, the uncompressed size here, 27 gigabytes. I can see the file size there. Let's say I want to know what that is. Above, the size was 75 megabytes. We'll take that, and we'll divide that by its current file size. And when we see the image was compressed at 40-to-1. And if we were to do that for our big one that I showed you, I'll just run those numbers through the Google calculator here. I'll just say 26.9 gigabytes divided by 0.8 gigabytes, and we'll see this was compressed 15-to-1. 15-to-1. So there you have it. That is compression ratios in a nutshell there. And of course, keep the questions coming. It's now the time for questions, and I do see questions in the chat. I'll leave this up here with my name and my email address up there for you to ask me questions. At this point, we've covered all the ground that I wanted to cover today, and I so appreciate everybody coming. I'm going to answer some questions now, so stick around if you want to hear these questions. And again, this webinar has been recorded. It's just later from our website. And here we go, stupid questions, and I'm going to get right to all these questions here, see what we got. All right, up at the top here. So let's see. One of the questions here is, how did we get the pixel width again? Well, again, it's just a grid, so the pixel width is just the number of pixels go across the image. So it's reported here here, the image width is just reported right there. It's just the number of pixels that go across the image. And the height, of course, is the number of pixels that go down the image. And that just refers back to this grid idea that we were talking about here. So we've got 7 pixels here and 4 pixels down. So the width would be 7, the height would be 4. And there's a question here, is there a way to convert a lower resolution image to a higher resolution image? Well, sort of, you could, but you're never going to get more detail. It's kind of the joke that we have when you're an image technician, you watch X-Files or you watch CSI or something like that, for example, and they say enhance, 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 and they have this blurry image and they go and they enhance the image. You know, at the heart of it, it's impossible to enhance the resolution of an image, to get more detail out of something that's fuzzy. You know, there on the screen, this little raster grid that I have, no matter how much I zoom in, it's always going to have these blocks. I mean, it looks better zoomed out, and maybe with our eyes, we hear that this is a triangle, and we could maybe even smooth out those edges with eyes, and we could kind of come up with some guesses what that would look like, and make it sharpen as vector images, and so we'd be able to do that. But in reality, there's really no way to enhance the resolution. When you do so, kind of do it, but you just get a smaller width and a smaller height. I hope that kind of answers that question, but I guess I would say that, you know, it's something that you could do, but it doesn't really make sense in a lot of cases. So we have a question from someone who's talking about flight missions. Flight missions aren't always flown at the same altitude. In this discussion, are we assuming the imagery has been corrected for errors or differences in scale? And yes, in this particular discussion, we are working with what you would call an ortho rectifier. The image has already been corrected for all of those things, the altitude and errors and things like that. And now we just have this grid, this raster image that has been ortho-rectified. Another question I see here is, why would an image have no data values of 0, 0, 0, or 255, 255, 255, or 254, 255, 255? Is that a bad image from the vendor? That's the question. And the answer is that because most commonly images are made up of 3 bands. And so, you know, when you use those comma-separated values, 255, 255, 255, what that means is, and I'll zoom right in here to my little pixels, and all the way in here, that's 255, 255, 255 right there. That would be the comma-separated bands. They're referring to white when they say that, or when it's 0, 0, 0, they're referring to black. That'd be 0, 0, 0. So what we're saying is, we only have 3 bands, and we only have this range of values. Let's choose one of these values to represent no data. Now, this only, of course, when you have an alpha band. In alpha band, you can have an alpha band that specifies transparency. But if you don't have that, you have to choose one of those pixel values to represent no data. Then people choose would be 0, 0. That'd be black. That's one representation of no data. And what that means is that you put in the metadata of the image, you say, look, means no data. And that's the viewer, in this my G-Express, that will black, and it's not black in this pixel. In this image, especially in these areas here, because the grid keeps going up, even no visually valid image here. The width is actually goes to here. All this black in here, we data. Look, that's if I want to put this image on top of another image, those pixels, and with the pixels from the image underneath. That's why we have no data values. That's why we do that, because we're only working with 3 bands. However, the best way, the optimal way, is to obviously work with an alpha band so that you don't have to have no data values, so that you can just tell the viewer, hey, use this alpha band for transparency. So when I'm mosaicing, when I put this image on top of another image, then the alpha band says, oh yeah, this is transparent here, this is transparent over here, And you don't even have to worry about specifying losing a color value, basically. Because it could, there are obviously going to be black pixels within the image. I could zoom in and find some black pixels in here, and we don't want those replaced. We don't want those transparent necessarily. So it's more optimal to use an alpha band. So I have a question about formats here. So what the difference is between both JPEG and format types. One of them is called JPEG 2000 Part 1, and the other has a bunch of letters in the name. Okay, so let's take what they're talking about here because we have an example of this. I'll pull my file formats 2000 Part 1 and with a bunch of letters in it, and those letters are GML JP2. Now, GML stands for Geography Markup Language. That's a specific type of metadata that is really XML. And so images aren't just the raster grid. They all have a bit of metadata. One type of metadata that I showed you guys was that coordinate reference system. Another might be in the metadata would be transparency value, like we just talked about. The no data value. Things in the metadata might be, what kind of camera took the picture, things like that. But GLJP2 is a way of representing that metadata. So it's a very good way of representing geographical metadata. And it's an open standard that's published by a standards organization responsible for these kind of things. It's the standard, a way for software applications to be able to read geospatial metadata in a common way and write geospatial metadata in a common way. And JPEG 2000 Part 1 is just a different way of presenting that data. Kind of software you want to use, but hopefully that helps. So what comes in here is what information of the image is compressed. How does the software compress the image? So it's a very good question, and it's something that we could do a whole other presentation on. But you can think of off the top of your head ways of compressing information, and you think of other compressed formats. You think of zip, for example. Zip file compresses data. You can throw all your documents in a zip file, and it compresses them, and then at the other end, someone can unzip that, and they have the exact same documents. No information has been lost or anything like that. So that's what we would call a lossless compression, where information is lost. Well, there's also something called lossy compression, where information, and you can't get it back. I see a question later on that says, can the original image back? Yes, in a way, but it's not exactly the original image. If you do a lossy compression, you're going to get a representation of the original image, depending on how much loss and how much compression you decided to go for. Now, it just depends on the file format for how the compression is done. If I were to think of a basic compression of a text file, for example, let's say I had a sentence, and the sentence is, "Hello, how are you doing today?" I could look for redundancies. I could look for repetitive letters, and I could look for repetitive words. So with a sentence like "Hello, how are you doing today?" there's not much that, as far as redundancy goes. But if I had a huge paragraph, or if I had a novel, if I had a Shakespeare play, I would have a lot of redundancy. So every time I saw the word look, I could replace that with a small symbol, maybe replace that with a capital L or something like that, and use less bits to represent that data. And so that would significantly shrink the size of data. So there's just one compression example, and we will get into others in different presentations. But I just wanted to give you that example, and that example I gave you is a lossless compression, because obviously every time we see a capital L, we just convert that to love on the other end, and we have all of our information back. We didn't lose anything. So there you go. And let's look at some other questions here. I think that might be all the questions that we get to answer now. We're kind of running out of time. But I do want to answer your questions by email. If you feel like sending them to me by email, let me put that back up on the screen. there are here. A lot of questions came in. I love that you guys have questions. It makes me feel good because I know that some of you were listening, and that's so. Again, this will be on both on our YouTube channel and available on our www.lizardtech.com under, I believe, news and events, something like that. And thanks, everybody. I appreciate your comments. I see a lot of nice comments in there, and I hope that you presentation. I hope you got a lot of it. And again, please view the recording. Please email me if you have questions. If I didn't get to your question, please email it to me. I'll be happy to respond. Thanks so much, everybody. I hope you have a great week and a great weekend. And that's all for now. Take care.